Hello, all, and welcome back to our second session on geodetic surveying. In our previous class, we discussed about various concepts in geodetic surveying, including principle, classification, selection of baseline and stations, orders of triangulation, triangulation figures. In today's class, we will be seeing something called as towers and signals and how to select a site for a baseline and reduction to center. Now, here we discussed about the definition of triangulation survey in the last class. To brief you about it or to revise you, we have 3 points A, B, and C. Let me take example of A as Bangalore, C as Mysore, and B as Mangalore. If I'm supposed to find out the distance, the definition states it is all about finding out relative or absolute position on the Earth's surface of a system of widely separated points. It is clear from the sketch that A, C, and B are widely separated. Now, how do I find out relative distances? It is in the terms of lengths and azimuths. That is, the length between AC, the length between BC, and the length between BA is found out, and azimuth as in the elevation. Coming to how do I find out absolute positions are what is the latitude of Bangalore, longitude, and at what height is it above mean sea level, and finding out latitude, longitude, and above mean sea level elevation of Mysore. By finding out these things, I can easily, not just me, anybody can easily find out the distance AC, CB, and BA. Now we saw why do we have to carry out triangulation survey, that is to say the objects. We saw classification, various components indicating the classification, various figures associated with it, criteria for selection of a figure. We saw what are the various, I hope you have found out what is a gridiron system and central system used in triangulation survey. We also saw what are the various steps associated when one has to carry out triangulation survey, and we ended our session with how to select a triangulation station. Before going ahead, let me stop at this point. We discussed triangulation, how to select a triangulation station. That is, triangulation stations should be intervisible, well conditioned triangle, easily accessible, neither too short nor too long, to be in a commanding place. Cost of cutting and filling should be minimum, and line of sight should not be passing over towns and factories. Coming to today's discussion, let us start with towers. What are towers? Towers are the structures. Here you can see a component wherein 1, 2, 3, 4, 5, 6 persons are standing. The final structure should be looking in this manner. Now, what is a tower? Tower is a structure erected over stations to support instrument and observing party. Why do we have to support instrument and observing party? When the station or signal or both are to be elevated. That is, say if I have to find, if the station points are Bangalore and Mysore, and you are supposed to see the point situated at Bangalore from Mysore, you need to have an elevated point. So thus comes the picture of a tower. Now, the triangulation towers are to be built in duplicates, and it should be entirely independent of each other. What do I mean by saying built in duplicates? In this sketch, you can clearly see this is the outer component and there is an inner component. Always the inner component or the inner tower will support the signals, and the outer structure will be supporting the observing party. Now, it may be built using timber, masonry, or steel, depending on the elevation to which the tower needs to be raised. Coming to signals, signals are structures erected to define the exact position of an observed station. Why do you have to erect it? So that from any point, the exact location of the triangulation station is clearly visible. Now, these signals are classified into non-luminous signals and luminous signals. Non-luminous signals are pole, target signal, pole and brush signal, and beacons. And luminous signals are called as heliotropes. Going ahead, we have something called as selection of site for baseline. Why do we have to break our heads to select a site for baseline? The measurement of baseline constitutes a higher accuracy component in a triangulation survey. Since the length of baseline needs to be measured with highest accuracy, the site chosen for baseline should meet certain conditions. Now let us look at various conditions that the site should be satisfying. Baseline measurement forms the most important part of triangulation survey. Hence, the site should be fairly level. It helps us in horizontal measurement without any corrections to be applied. And if at all you come across any sloping ground, make sure that the ground is uniform and gentle. And at no point undulating ground should be chosen for a baseline. So we have to avoid undulating ground as much as possible. The next point is the site should be free from obstructions. Why should this be happening? So that there is no hindrance in measuring the distance between starting point and ending point. Also, the cost of clearing, the labor required to clear, and the compensation for the lands in between the stations should be as much minimum as possible. The extremities of the base should be intervisible at the ground level. The ground should be reasonably firm and smooth. Water gaps should be avoided as much as possible. And if at all one comes across water gaps, it should not be wider than one chain length. The site should suit extension to primary triangulation. What is meant by extension to primary triangulation is, if AB is the baseline chosen, if need arise to extend AB beyond the distance AB, that is to point E or point H, the site should provide this option for the surveyors. This is one example wherein AB is set up. Now going ahead, we have next and last concept called as reduction to center and satellite station. Before going to what is reduction to center, let us see what is a satellite station. We generally choose satellite stations such that it is at the highest elevation or top position, such as church spire, steeples, flagpoles, etc. Now, if we have chosen these points as triangulation station, how do I set up the equipment on it and measure the angles? That is, it is not possible to set up the equipment to measure the angles and distance. Now, if this is the case, we choose a temporary station very close to the triangulation station and call that as satellite station. Now, in the figure over here, A, C and B are the triangulation stations, and let B be the point where we have church spire, steeples, flagpoles or temple tops, etc., wherein one cannot establish the equipment to measure angles and distance. In this case, I choose a station S very close to station B and make all the measurements to point S and find out what would be the value of alpha if the equipment was kept at point B. Now, how do I do this? The main thing is we can easily measure the distance BS, which is called as a small d. The distance AC can be computed based on the previous length computations. At point A, when the equipment is kept at point A, I can clearly cite point C and point B and measure angle CAB. And when the equipment is kept at point C, I can clearly measure angle A, C and B. Going ahead, the same thing is being given over here. Reduction to center is nothing but when all the readings from S is brought back to what would have been the value of alpha if the equipment was kept at point B. It is computed at 3 stages. In the first stage, we will find out the distance AB and BC. In order to find out the distance AB and BC, let us consider the triangle ABC. In the triangle ABC, the only distance known as small b, and we know the angle CAB and ACB. With these knowns, I can compute BC, which is nothing but small a, as small b into sine of CAB divided by sine of ABC, and AB, which is nothing but small c, to be equal to small b multiplied by sine of ACB divided by ABC. For computation at this stage, we can assume that angle ABC will be equal to 180 minus CAB minus ACB. That is, only for this point we will be assuming it to be 180 minus CAB minus ACB. Now one may ask, why do all this jugglery when you can directly take it as 180 minus this? Since the accuracy and precision required while computing angles and distance is very high, we cannot take any risk, and a corresponding point will be chosen as satellite station, and it will be reduced to the value required. Now, doing this first step, I have found out the distance of small a and small c. After finding out small a and small c, next step is to find out the angle beta 1 and beta 2. That is the angle at point A and at point C subtended between B and S. Now, how do I find it? The only known points are C distance and A distance and the small d. So, I can consider ABS. In this ABS triangle, sine of beta 1 will be equal to SB, which is nothing but small d, into sine of theta plus gamma divided by AB. AB is nothing but small c. Similarly, if I consider triangle CBS, the known value is D and unknown is beta 2. So sine of beta 2 will be equal to SB into sine of BSC divided by BC. That is nothing but D into sine of gamma divided by A. When I compare the distance of AC, AB and BC, the distance SB will be very small. Since the distance D itself is very small, the angle subtended at the base will also be very small. That is, beta 1 and beta 2 will also be very small. So divide this entire equation by sine of 1 second. On dividing this entire equation by sine of 1 second, the equation gets converted into beta 1 to be equal to D into sine theta plus gamma divided by C multiplied by 20625, and beta 2 will be D into sine gamma divided by A into 20625. Now the third step is, after computing beta 1 and beta 2, the observed angles theta at S is reduced to that of alpha at B. That is, from this angle, from the angle theta, beta 1 and beta 2, I'll reduce it to angle alpha. How do we find out angle alpha? The angle ABC, which is angle alpha, will be equal to angle AOC minus beta 2. How do I come across this component? Is the angle BOC will be equal, that is, this angle will be equal to 180 minus of alpha plus beta 2. Now, what will this angle be equal to, which is nothing but AOC? AOC will be equal to 180 minus of 180 minus beta 2 plus alpha. 180 gets cancelled, and minus is equal to plus. Hence, my final equation will be equal to angle AOC will be equal to beta 2 plus alpha. Now the unknown over here is angle alpha. So angle alpha will be equal to angle AOC minus beta 2. But in order to find out angle AOC, the other components that I know is beta 1 and theta. Similarly, just like the previous case, angle AOC will be equal to beta 1 plus theta. Substituting that in the equation, alpha will be equal to theta plus beta 1 minus beta 2. The case does not end over here. It is not necessary to place the satellite station always to the left of the triangulation station. It can be placed anywhere in this 360 degrees. Now, in order to do that, we split it into 4 different cases. Left of station, right of station, north of station, and south of station. If the satellite station is to the left, the value alpha will be equal to theta plus beta 1 minus beta 2. If it is to the right, it will be theta minus beta 1 plus beta 2. To the top, it will be minus theta minus beta 1 minus beta 2. And the bottom or the downwards, it will be plus beta 1 plus beta 2. This constitutes the entire components in a geodetic survey. Going ahead, what are the probable questions that one may be asked at the end of triangulation survey? What is a triangulation survey? How is it classified? What are the various figures in triangulation survey? What are the criteria to choose a triangulation figure? Criteria to select a station? To choose a site for baseline? What is a satellite station? And briefly explain reduction to center. I hope you can answer all these questions. Thank you.